Hey, what's going on, everybody? We're going to get started here with some nuclear chemistry. I hope everything is going well in your neck of the woods. Um, and yeah, let's get right into it. So today's lecture is on nuclear energy. The reading is Atkins Focus 10, Part C. And then if you want to see what homework is due, just make sure you check Learning Suite, check your emails, stay on top of things. We're going to talk today about energy, nuclear binding energy, and we'll discuss fission and fusion and mass defect, which is a way of relating energy to matter using Einstein's equation. And then I'll end with a cautionary tale, the radioactive Boy Scout, which I hope you'll find interesting. I really did, and I wanted to share it with you. New skills, you should be able to calculate nuclear binding energy from nuclear mass. And hang on just a second, because I wanted to, just don't mind me for a second here. Okay, we'll calculate nuclear binding energy from nuclear mass and calculate the energy released in nuclear fission reactions. First, a thought. This comes from Kim B. Clark from October 2015 conference. He says, life may get hard, confusing, painful, and discouraging. I bear you my witness that through the companionship of the Holy Ghost, the light of the gospel of Jesus Christ will cut through the confusion, the pain, and the darkness. Whether it comes in a remarkable burst or in a gentle flow, that glorious spiritual power will infuse healing, love, and comfort into the repentant, wounded soul. Dispel darkness with the light of truth, and cast out discouragement with hope in Christ. We will see these blessings come, and we will know by the witness of the Spirit that it is the Lord Jesus Christ working in our lives. Our burdens truly will be swallowed up in the joy of our Redeemer. And to accompany this, Light Conquers Darkness by Nicholas Roerich. Okay, so next up, I know it's not Chris Hemsworth, but isn't he cute? This is thorium. We're going to talk a little bit about thorium, naturally occurring radioactive material named for the god of thunder. So first we'll talk a little bit about nuclear energy. And we have talked a lot throughout this class about how chemical reactions can occur and release chemical energy. That's driven by two processes. First, the spreading out of matter and energy, which we call entropy, and then the generation of heat, which we call enthalpy, which increases the entropy of the surroundings. Okay, but we're going to talk a little bit about nuclear energy and how that's a little bit different. So if you want to compare chemical energy to nuclear energy, you want to think about, say, the amount of energy that's released from the combustion of gasoline. And that's on the order of, 5.5 times 10 to the third kilojoules per mole for gasoline. Well, let's look at a fission reaction where you've got uranium-235 that accepts a neutron and splits into krypton and barium isotopes and generates 3 neutrons. This has an energy of 16 times 10 to the 9 kilojoules. So we're talking 1 million times more energy per mole from a fission reaction relative to a combustion reaction. Huge difference. Fusion is a process where you've got 2 nuclei and you are combining them into a single nuclei, and that releases an awful lot of energy too. Again, like millions of times larger. Okay, so wow, if you do a plot of this, which my friends at XKCD have put together here, there's a fuel energy density in megajoules per kilogram. And so this is a combustion of sugar, coal, fat, gasoline. And then you have the energy density of uranium, which is off the charts and filling up multiple pages. And then the The quip here at the bottom is log scales are for quitters who can't find enough paper to make their point properly. All right, so matter and energy. There is this relationship between matter and energy that makes nuclear reactions so much more powerful than chemical reactions. And they're related through Einstein's famous equation E equals mc squared. So the idea is that you have energy related to mass, and so the amount of energy that is released from some process, even a chemical process, takes some mass with it because there's a relationship between the two. So for a chemical reaction, say something that's 1,000 kilojoules, then the difference in mass between the products and the reactants is negligible. It is 10 to the minus 8 grams difference in energy, but it is still real. Most of the time we don't care about that and we just say mass balance, the mass of the products is equal to the mass of the reactants. And generally that's true, but when you get into nuclear reactions, it's a little bit different. There is a huge difference in the energy that is released in a nuclear reaction. And because of that, the relationship between matter and energy is significant. So how does that manifest itself? Well, we can think about the binding energy of the nucleons, the protons and the neutrons in the nucleus of an atom. And those are pulled together by the strong nuclear force, which causes the binding of these different components in the nucleus. When they come together, then energy is released. So if you've got all of these nucleons separated and they come together, there's a binding energy that holds them together and it releases a ton of energy when that happens. That energy can be related to a mass difference between the nucleus and the separated nucleon. So if you measure the mass of the nucleus and you measure the mass of the separated nucleons independently, there is a difference there, and it's substantial. We can measure the mass of the products and the mass of the reactants. So the mass of the nucleus and the mass of the individual nucleons. And so for iron 56 with 26 protons and 30 neutrons, this ends up being a change in mass. And so you're going to look at the mass of the iron nucleus minus the mass of the individual constituents of that nucleus. All right, so the mass of iron 56 is actually 55.921 AMU. These are atomic mass units. So this is the mass of one single nucleus. We'll talk about how to convert that into kilograms on a little bit later. But then you have the mass of all of the protons. You've got 26 of those, and the mass of proton is 1.007 AMU, plus the mass of all of the neutrons. So there's 30 of those. And so you get a difference in mass. And typically for mass defect, we're looking at just the absolute value because we want to see the energy difference. And this is 0.531 AMU, which if you think about it, that's like 1% of the mass of the nucleus. Well, that's pretty significant mass difference. And we can calculate the energy, the binding energy of this process, the energy that's released when these nucleons come together. So that's the mass. And then we'll convert the AMU into kilograms. And the reason that we're doing that is because a kilogram meter squared per second squared is a joule. So we end up with 7.92 10 to the minus 11 joules per nucleus. And that ends up being substantial for a mole of these nuclei. Okay, and just to make the point about this conversion, 1 joule is equal to 1 kilogram times meter squared per second squared. So that's the conversion that you're going to use in order to get to joules from this mass defect equation. Okay, all right, so the binding energy per nucleon actually is a pretty important value for comparing the stability of different nuclei. So you can measure the binding energy of helium per nucleon and the binding energy of iron and uranium. You'll notice that the binding energy per nucleon is a little bit different. The binding energy per nucleon for iron is actually greater, which means that this nucleus is more stable than either helium or uranium. Okay, so we can calculate that from the data from the previous slide, and we get essentially the same number that they got there. All right, so what does that mean for all of the other elements too? Well, if you plot the binding energy per nucleon for all of these elements, you'll see that that the binding energy per nucleon for the really light elements is not so great compared to, say, iron. All right, iron has the most binding energy per nucleon of all of the elements, so it's the most stable nucleus. So if you have things that are bigger than that, these are going to tend to break up into smaller pieces until they get to the most stable binding energy nuclei down in this area right here. Okay, that smaller nuclei, on the other hand, they will undergo fusion in order to fuse into nuclei that are closer to iron. Okay, so on this side, these things are going to tend to fuse, and then on the other side, the larger nuclei are going to undergo fission and the smaller nuclei. Okay, all right, great. So so most things are going to want to come down to the iron if you've got a nuclear reactor and you've got all these processes happening, like in stars. And so a lot of stars have a substantial amount of iron there because you can have these fusion and fission events that go on. Okay, so let's do a quick quiz. Let's look at the mass defect for oxygen-16. 1.37 times 10 to the minus 4 kilograms per mole. What's the binding energy per nucleon for oxygen-16? Okay, and you've got Einstein's equation here, and you've got the speed of light. Okay, so I want you to pause and calculate what the mass defect, or what the binding energy per nucleon is here. And then we'll go through it here in just a sec. Okay, all right. So remember that 1 kilogram times meter squared per second squared is 1 joule. That's going to become important here when we start calculating the energy from the mass defect of oxygen-16. Okay, so the mass defect goes here, and the speed of light squared goes here, and then we calculate something like 1.23 times 10 to the 13 joules per mole of oxygen-16. Now, we're not done yet because we want to get the binding energy per nucleon. Okay, so in 1 mole, we have 6.022 times 10 to the 23rd atoms, Avogadro's number. And for every atom, we have 16 nucleons. If you crunch this all the way through, then you get 1.278 times 10 to the minus 12 joules per nucleon. Okay, all right, so let's go on. Let's talk a little bit about nuclear fusion reactions. Okay, so one fusion mechanism uses deuterium. So deuterium is hydrogen with an extra neutron. And if you've got 2 of these deuteriums and you get them close enough together where their nuclei can interact, then they will generate helium-3 and then an extra neutron and then a whole lot of energy. So you've got this fusion event of smaller nuclei going into larger nuclei. So this can go through a few different steps, and all of them result in the involve the fusion of 2 smaller nuclei into larger nuclei and the release of a substantial amount of energy. Okay, so the overall reaction releases 3 times 10 to the 8 kilojoules per gram of deuterium. That is huge, huge energy density, and it's the same amount of energy that the Hoover Dam processes at full capacity every hour. So think about the amount of water that has to move through this dam in order to generate the same amount of energy that is stored in 1 gram of deuterium. Now, if we could do that, if we could fuse deuterium efficiently, it would be fantastic for energy. All right, so let's talk a little bit about nuclear fission now. In 1938, Meitner, Hahn, and Strassman took heavy atoms like uranium and they just hit them with neutrons. This split the atoms into smaller fragments. These are called fission reactions, and they release huge amounts of energy. So you got a neutron, hits the uranium-235 in this case, which causes reorganization of the nucleus, which is unstable, and now it becomes more stable by splitting into two and then releasing some extra neutrons. So let's do a practice problem here where we're looking at the amount of energy that is released from 1 gram of uranium-235 that undergoes a fission reaction. Okay, so uranium-235 bombarded with neutrons, they split apart in a variety of ways. It's like glass balls that shatter into pieces of different sizes. In one of these processes, uranium-235 forms barium-142 and krypton-92, and then a couple of extra neutrons. So what's the energy in joules released when 1 gram of uranium-235 undergoes this fission reaction? The nuclear masses of the particles are given to you here in AMU. And so think about process for how you do that. It's going to be very similar to what we did before. Instead of calculating the binding energy, we're going to look at the energy that is released by calculating the mass defect between the products and the reactants, and then use Einstein's equation to get the energy that's released from this process. Okay, so we'll use E equals mc squared. Remember that your mass needs to be in kilograms so that you get joules for your energy. And then we'll need to find the total mass defect, delta mass. And for the mass, we're going to find the mass of the products and the mass of the reactants. Now, it's nice because we already have the mass in AMU of each of these nuclei and for the neutrons. Okay, and then just remember your conversion for AMU to kilograms. Okay. All right, so the masses of the particles, we'll calculate the mass defect first. Here are the masses of the particles. We've got the products. This is the mass of our barium. This is the mass of our krypton, and then the mass of our 2 neutrons. So this is the mass, total mass of our products, and then the sum of the masses for our reactants. We have a number that's slightly different. Okay, so that difference then is our mass defect. This is 0.19 atomic mass units. And we're going to calculate that. Let me move me out of the way. We're going to calculate, we can get that into kilograms pretty easily using the conversion. Okay, so we've got our mass defect. Now all we need to do is find what the energy is. Okay, well, I didn't mean for all of this to show up all at once, but we want the energy released in the fission of 1 gram of uranium-235. So we already calculated our mass defect here. And then the energy of just one nuclear reaction, if we just have one of these processes taking place, then we've got our mass defect times the speed of light squared. In 1 gram, and we have to report that in kilograms, we have n number of nuclei. Okay, so how many nuclei do we actually have there? Once we find the number of nuclei, we can multiply that by the energy per nuclei to get the total amount of energy that's released. Okay, so the number of nuclei is the mass of the total mass, 1 gram, divided by the mass of the nucleus in AMU. If we convert that into kilograms, then we end up with 2.56 times 10 to the 21 total nuclei in 1 gram of uranium-235. Okay, so that's how many nuclei are going to be irradiated and undergo fusion or fission. So then the delta E is the number of nuclei times the mass defect per nuclei times the speed of light squared, and we get something like 7.3 times 10 to the 10 joules. This is 673 gigajoules, and that's a million times more energy than 1 gram of methane. Okay, so what can we do with that? Well, one of the things that we can do with that, my floating head over to the other side, one of the things that we can do with that is we can generate lots of heat. And heat is useful for converting water from liquid to steam. And that steam can be used to do useful work, like turn a turbine and generate electricity. So we can use nuclear energy to do this. So this is pretty standard. You could use coal to do this too, to turn water into steam. But in this case, the heat source is a nuclear reaction. And so a nuclear reactor, turn your attention to this over here, a nuclear reactor consists of enriched uranium fuel rods that can undergo fission and release lots of energy. And the fission is driven by the absorption of neutrons from some other source. All right, and so you can control this reaction with control rods by putting them in between the neutron source and the target for the nuclear reaction. So those control rods are critical for controlling how quickly this reaction happens. And if you didn't have any control rods in there at all, then everything would happen all at once. All of this energy would be released much faster than this power generator design could sustain. And so what happens if it goes out of control is that it completely melts down and literally melts down. There's enough heat generated that it can destroy all the containment apparatus here and the nuclear power generator. It's a big mess. Okay, but if that can be properly controlled, we can use nuclear energy for efficient power generation, really powerful, high energy density energy conversion, and then no carbon emissions, right? Fantastic. And if it's properly contained and controlled, this can be very clean. All right, but that is the caveat, if it's properly contained and properly controlled. So I'm going to change gears a little bit and talk about a cautionary tale about what happens if this is not properly controlled or contained. So this is the story of David Hahn, radioactive Boy Scout. And there's a really great article. You can read all about this, Harper's Magazine, November 1998. It's a great article by Ken Silverstein. You can find that online. There's a PDF version, but really, really interesting story about a high school kid who wanted to save the world's energy problem. So his heart's in the right place, but there were some things that he wasn't ready quite to deal with and didn't have expertise to deal with. We'll talk about that here. So he was born in 1976. At age 12, he was reading his dad's college chemistry book. A bright kid. At 14, he was making nitroglycerin in his bedroom. He ruined his carpet, so his parents banished all of his chemistry experiments to the basement. But a little later, when he was 14, he was awarded the Atomic Energy Merit Badge, and he wanted to save the world's. He wanted to solve the world's energy problems for his Eagle project. Yeah, it's a good thing. At age 16, this is what really set him on his way. He got a job. He got a Burgundy Pontiac 6000. And he got a Geiger counter, which he assembled himself and mounted on the dashboard of his new car. And then he had a quest. And that quest was to build a nuclear reactor and start generating energy using nuclear reactions. At 17, he created a nuclear breeder reactor, and we'll talk about what that is, and also created an EPA Superfund site in his mom's backyard, which was probably not what he was aiming for. And we'll talk about kind of how that happened. So we just talked about nuclear fission, and nuclear fission can be used as the fuel in nuclear power plants. So there's two flavors of this: uranium, which comes in uranium-238, which is non-fissile, which means it is not fissionable, doesn't undergo fission, and then U-235, which is a little less than 1% of the naturally occurring uranium. But with U-235, a fission chain reaction is possible. It's driven by the absorption of one neutron to generate different fission products and some extra neutrons and a lot of energy. Now, another way to get to start a fission chain reaction that could be useful for generating lots of heat in a nuclear reactor is, well, let me talk about this for just a second. So the chain reaction is possible because if you've got U-235 and you hit that with a neutron, it becomes U-236, which breaks up into two different parts and then generates 3 more neutrons. Now, if there's more U-235 around, that can be a good target for these neutrons, and the process can continue. And so because each one of these generates 3 neutrons, there's a possibility of this reaction going 3 more times. And each one of these can do the same thing 3 more times, up to 3 more times. And so this chain reaction can be really efficient in terms of releasing energy very quickly. Okay, so another nuclear fuel is plutonium, and that's generated from uranium-238. So it's produced by absorbing a neutron into U-238, which goes through a couple of different processes, and then it ends up with plutonium-239 plus a couple of beta particles. That's the production. The reaction step is that it absorbs a neutron, just like U-235, absorbs a neutron, and it generates plutonium-240, which is extremely unstable and instantly degrades into fission products and a lot of other neutrons. And so it can also produce fission chain reaction, which is useful if you're using it to generate electricity. And that was this kid's dream. He wanted to build a nuclear reactor. I'm going to say how not to build a nuclear reactor for the steps that he followed here, but he did some good things, doing some research in the library. He made some friends with some people at the Nuclear Regulatory Commission who were very helpful at giving him information that helped his dream become a reality. Scavenged for supplies and radioactive materials. Obviously, you can't just go down to the hardware store and pick up a bunch of uranium. And so he came up with some strategies to collect those materials, and then he built a nuclear reactor. And then he built a nuclear breeder reactor, which you can use to make your own nuclear fuel. And when I say your own, I don't mean your own. Don't do this. But this is what his plan was. Okay, so the first thing is, how do you make a neutron gun that you can use to irradiate materials that will undergo fission? So one place to start is americium-242. He thought this was a good place to start because you can get americium-242 from broken smoke detectors. And so he bought 100 broken smoke detectors for about $1 a piece from a company, and then found the way to extract the americium. And then he took that and he put it into a block of lead. So you got a block of lead with a hole drilled out in it, and then put the americium down in the bottom so that the alpha particles come in just one direction. So the americium decays by alpha decay, but he doesn't really want alpha particles, he wants neutrons. So he puts aluminum foil on top of there, just cover things with aluminum foil, but that turns out to be a good absorber of alpha radiation, And as it absorbs alpha radiation, it emits neutrons. And then those neutrons can go to hit a fission target. So the target, he wants some fissionable material like U-235 or thorium-232, and we'll talk about how he got his hands on some of that. But he needed to test it, and because neutrons aren't really detected by a Geiger counter very well, he had to come up with a different strategy. Geiger counters can sense protons, and as a result of his research, using paraffin wax and irradiating that with neutrons, you get negatively charged wax, and then it starts to emit protons, which you can detect with the Geiger counter. So he was really excited when he found that his neutron gun was actually emitting neutrons. Okay, so finding fissionable materials. After doing some research, he found that he could use his Geiger counter to find pitchblende, which is a naturally occurring uranium ore on the shores of Lake Huron. So driving around Lake Huron in his Pontiac 6000 with his Geiger counter, found some sources of pitchblende. He wasn't real satisfied with that, so he wrote to the Nuclear Regulatory Commission, which was happy to supply him with information about a Czechoslovakian firm that sells uranium oxide. As it turns out, the NRC didn't know they were talking to a 16, 17-year-old kid in high school. They thought they were talking to a professor at the local community college or a physics professor at Chippewa Valley High School. So, that was his strategy for convincing people to give him information. He purified uranium with homemade nitric acid, and then he also looked at generating thorium, which can be found in Coleman lanterns. Thorium is a naturally occurring radioactive material, and they used to use it in Coleman lanterns. Now they use yttrium, which is probably a good idea. Now, one of the problems with thorium from these Coleman lantern mantles is that it's thorium oxide, which isn't as good as pure thorium. But he found out that he could do some redox chemistry and use lithium extracted from lithium batteries. And so with lithium and thorium oxide and a lot of heat, he generated thorium metal and lithium oxide. And using this process, he refined his thorium to 9,000 times more pure than you can find in nature and 170 times greater than the NRC licensing level. So he's breaking all kinds of regulatory laws right now. But he did get thorium-232, and he started to irradiate it with neutrons. The idea was to generate uranium-233, which is fissile material. Okay, so neutron gun 2.0. As americium just wasn't given enough neutrons to do anything useful with. So he started down a different path, looking at radium-226 and using beryllium as his neutron generator. So radium, how do you find radium if you're a 17-year-old kid? Well, he drove around town with his Geiger counter, and it went crazy when he drove past an antique store. So he stops, he goes in there, he finds an old clock that he talks him down on the price. He's found $10 for this old antique clock. And when he gets it home, he finds an old can of radium paint in it. So this is the jackpot for this kid. And he uses that radium, purifies it, and then he packs it into another lead block that he can use as his alpha source. And then his neutron generator, he's reading, oh, well, beryllium, that's even better. So a friend of his who's in college borrows a chunk from the local community college, and that's what he uses as his beryllium sheet here. So what's he going to do with that? Well, he's going to hit thorium-232 and generate radioactive products. And he noticed that when he did this with the thorium powder that he was using became more and more radioactive. So more clicks on his Geiger counter. Unfortunately for him anyways, the uranium was giving some disappointing results and it didn't seem to be doing anything. So what's going on with the uranium? He sends a letter to the NRC, and they helpfully inform this Professor Hahn, that his neutrons are going too fast. The neutron sources can generate neutrons that are moving at like 17 million miles per hour. If you slow those down, it dramatically increases the probability that these neutrons will be absorbed by uranium. Well, how do you do that? One way to do that is to use tritium. Where do you get tritium? Tritium is hydrogen with a couple of extra neutrons on it, and it is radioactive. But it's found in luminescent gun and bow sights. So he starts ordering these things and extracting the waxy substance that contains tritium, and he coats the beryllium neutron generator with this tritium material. So this ends up actually improving his uranium fission yield. And so he's got uranium-235 plus a neutron, and he's starting to get fission products plus more neutrons, and things are really starting to heat up. It's not enough for a chain reaction. That's when he gets this idea. He's like, okay, all right, I'm gonna make a breeder reactor. So what's a breeder reactor? Well, a breeder reactor is where you have some core that is radioactive material, and it's generating a lot of radiation, including a lot of neutrons. And this is your fuel. So in addition to generating the neutrons, it's also generating lots of heat. But the nice thing about this, if you want to make your own breeder reactor, is that those neutrons can be used to irradiate something else. So he's got this seed fuel. He's got uranium-233, which he's made from irradiated thorium-232. And he's combined this with his americium and radium and aluminum and beryllium to generate the neutrons. And then he wraps the whole thing in aluminum foil. Okay, that's his seed fuel. So a breeder reactor also uses a blanket fuel. This is something that is not as radioactive. So in this case, thorium and uranium, including a lot of uranium-238. So he wraps this in aluminum foil too, and he places it next to the seed fuel. So he's got tons of neutrons being generated by his radioactive core, and then he's using that to irradiate uranium-238. Uranium-238, when it gets irradiated, it generates plutonium-239. And plutonium-239 can be recycled as a seed fuel to generate lots of neutrons. He takes the whole thing, the seed fuel, the blanket fuel, and he wraps the entire thing with duct tape. Okay, at this point, there's some danger because now he's not just irradiating one thing and generating a few more neutrons, and he is irradiating a large amount of uranium and generating a lot of radioactive material. He's doing all of this in the potting shed in his mom's backyard. Okay, so safety-wise, he's got a makeshift lead apron, and he's throwing his clothes away after he's done working with this stuff every day. But he notices that the radiation is detectable through concrete. So he's like, okay, I've got to control this reaction somehow. And so he uses neutrons, or he uses cobalt control rods to place between the seed fuel and the blanket fuel. And the cobalt is a good neutron absorber that will prevent neutrons from going from the seed fuel to the blanket fuel. So he can The idea is so that he could control this reaction. So what he did is he buys cobalt drill bits from the hardware store, and he's using that to place in between the seed fuel and the blanket fuel. But that wasn't enough. And he's noticing that after a period of time of allowing his reactor to work, he is generating more nuclear fuel. And he can pick up radiation 5 doors down. And at this point, he's saying, okay, I've got too much radioactive stuff in one place. I've got to do something about this. Well, he didn't do anything about it. But on August 31st, 1994, at 2:40 in the morning, police respond to a call and they find him waiting for a friend. This is pretty suspicious though. So they're like, we got to search your car. In the back of his trunk of his car, his Pontiac 6000, he's got a bunch of broken smoke detectors, mercury switches. He's got old clock faces. He's got a ton of chemicals and then old lantern mantles. But the thing that really concerned them was a toolbox that had a padlock on it, and it was sealed with duct tape. They're getting pretty suspicious about this. So they call the state bomb squad, and they call the health department, and they towed his car to the police station to investigate. So the good news is that they find out that this is not an atomic bomb in that toolbox. But the bad news is there's more radioactive material than is naturally occurring in the state of Michigan. So this triggers a federal radiological emergency response plan, and this means it's time to call the feds. So in addition to the local response, on September 1st, 1994, the Department of Energy is called in, the Environmental Protection Agency, the Federal Bureau of Investigation, and the Nuclear Regulatory Commission are all converging on this kid's car. It wasn't until November 29th, 1994, that they realized this is just the tip of the iceberg. The NRC and the EPA survey this potting shed in his mom's backyard, and they find a vegetable can, among other things, that's registering like 50,000 counts per second. This is 1,000 times greater than normal background radiation. But this is where it gets interesting. This was after his mom threw away everything in there into the municipal garbage. So this stuff just went to a landfill somewhere. And so David's like, they didn't even get any of the good stuff. All the good stuff went to the trash. All right, so they're trying to figure out what to do with this. January 25th, 1995, they realized that the leftover material that's in the shed is regulated by the U.S. Atomic Energy Act. And they designate the backyard and the potting shed as an EPA Superfund site. Superfund site, that's the kind of stuff that a Superfund site is like a huge environmental disaster somewhere, like, irresponsible corporations or a nuclear reactor that goes out of control, like Chernobyl. That would be like a Superfund site. This is the backyard of his mom's house. So June 26th to 28th, 1995, the EPA has to come in and clean this whole thing up. $60,000 to clean it all up. And they take everything that's left in the potting shed, they put it into 39 sealed barrels, load it up onto a trailer, and it's actually buried in the Salt Lake Desert. David Minar, who is the Department of Public Health radiological expert, said, "These are conditions that regulatory agencies never envisioned. It's simply presumed that the average person wouldn't have the technology or materials required to experiment in these areas." I mean, who would think that a high school kid could have access to all of this and do what this kid did? It was unbelievable. So take-home points, just a few. If your roommate's closet starts to glow, or if your boyfriend or girlfriend wants to mount a Geiger counter to their dashboard, ask questions, because you need answers at this point. It's more seriously, when you science, be careful. and be safe about what you're doing. There's a big difference between, messing around in the backyard with chemicals and doing this for a living. And when you realize that working with these chemicals and these materials that you're going to be working with over your careers is not just for a couple of months or a couple of years, but you start to take things a lot more seriously when you realize, hey, this is what I want to do for a living, and I want to be safe about it. I want to take care of myself and uh, be safe for me and safe for my community. The other thing I want to say is with great power comes great responsibility. So understanding how nature works, there is a lot of power that comes with that. Be responsible and use that power for good. All right. Well, I hope you've liked this lecture. Oh yeah, like and subscribe. And if you want to see more videos like this, send me an email and we'll just keep it going. Thanks, guys. Thanks for coming to my video channel. And have a great week and see you next time.